Hi, Mike Matchett for Small World Big Data, and we are here today talking about what's potentially the processor of the future. It's gonna be game changing. We've got Tachyum here today. I've got the CEO, the founder, the president, Radoslav Danilak. Welcome, Rado.
Thank you.
Um, we talked a couple years ago at Flash Memory Summit about what you guys were starting to do, but now it's time to talk about what you've done. And I think just to introduce a little bit quickly for our audience, can you explain what Tachyum's about in a thumbnail and what the technology is that you're bringing to market?
Yes, so Tachyum is bringing what we call first universal processor. What it means that today when customers are using microprocessor CPUs for applications, server applications, and web pages which basically customers are surfing, they use microprocessors for that. Then they use what is called GPU for supercomputing applications, simulate stuff and from chemical and mechanical stuff, and then it's used AI accelerator to basically use AI. And the AI is used when anybody looks at their Facebook web page. The recommendation of what are there are driven by AI. Finding people in the picture is done by AI and so on. And so AI is everywhere there. And so universal processor means that instead of having three different chips to solve three different problems, you can have microprocessor chips, a chip which can also do high performance computing and AI in single chip. So it's really not CPU plus GPU plus TPU or AI accelerator on one chip. Is really microprocessor which subsume the high performance computing and AI.
All right, so a new kind of architecture for microprocessors, in fact, a new microprocessor, universal processor. You have quite the staff working there at Tachyon, people who have advising you as well that have built ARM, that have built, even yourself, have built a whole chip families in the past. So it's it is very real, right? This is something that's we can look at all the technologies on. So folks, check it out and look for this. We are going to dive in just a little bit here. We're going to just scratch the surface of what this Prodigy chip does. It's going to be a little bit of a fast thing, but let's start with some of the challenges that you uh, faced when building this new architecture and had to overcome. So let's talk about the size and speed and scale. How did you guys manage to tackle those problems?
Yeah, so bringing new architecture to market is always challenging and is not straightforward, especially when you are bringing instruction set and new technology to the market. So the biggest thing what needs to company solve to basically lead to adoption of the chip is what kind of software can run on it from day one, how easy to have software on it, and how easy to integrate into existing system. So to address these issues and allow quick adoption, we allow to execute also existing 64-bit x86 or Intel AMD Linux binaries without recompilation or translation. Our telco customer, they can run ARM v8, and some academia can run RISC-V software existing on our platform, and we demonstrate that. So that is basically ensuring that from day one, when somebody gets our machine, you'll have native applications, what we give and we provide, but he can just download existing applications and run on it. So the software is the most important and determining factor in success of the architecture.
All right. So in order to support that, also that new architecture and really optimize things, you have a new way, new compiler technologies that go with this that match the architecture, right? But to keep that backwards compatibility with all the existing software, as you just said, lots of existing architecturally built applications can still run on here, making it smooth, which
And
is
and
good.
Yeah, and this is analogy what's happening with MacBook Air when Apple introduced M1 microprocessor, which is ARM-based,
Mhm.
and they provide the Rosetta software, which allows to run existing applications x86 on their platform. Apple did that also transition from PowerPC to x86 world. So the technology and concept is analogous to that.
All right, let's talk a little bit about what someone gets then out of the Prodigy chips here. You performance. Let's start with performance. What exactly can someone expect if they are now going to run systems based on Prodigy?
So what they can expect, relatively, the market leader with larger market share is Intel, and AMD, they have better performance per dollar solution by at least 30-40%, and they are gaining market share because of that. Relatively to Intel 8380, their high-end solution on spec in 2007 rate, uh, basically we see about 4 times higher performance. So for Intel chips, you can replace the single hour one for same performance. That's on spec-in or integer applications. If you look at supercomputer applications, the Intel A380 is about 10 times lower raw performance than NVIDIA H100, which was recently launched and will be shipping, sampling by end of this year and shipping next year. And NVIDIA chip is about 10 times faster than Intel. Now, relatively to NVIDIA H100, which has about 30 teraflops of performance, we are basically delivering 93 teraflops, about 3 times more. Now, if you look at AI in legacy applications, inference and training with dense calculation and 4 to 2 sparsity, they could see about 3x more performance for training or inference. However, super sparsity or sparsity and a higher, more efficient data type, the most customers for most application, they should see about 6x performance in AI inference and training. So these are very decent number, especially then our chip is smaller and lower cost than any of these competitors.
All right, so you are accomplishing this. I'm just looking at the spec sheet a little bit. You've got a chip with 128 64-bit processing cores running on there. How fast are those cores running?
They can run up to 5.7 gigahertz, and the more power efficient version, they run at 4.5 gigahertz at minimum voltage.
All right, and so that's pretty fast, right? And you run
That's
into, there's a
fast.
lot of tweaking you had to do to get something that fast to run at that density. Then part of the optimization is the way you handle floating point, obviously, the way you handle matrix and vector kinds of operations and bring them into the chip and the compiler who can uh, look ahead and uh, calculate data in the right places at a pre. I don't want to say what's the rest description of that pipelining, I guess.
It's not necessary pipelining. It allows better pipelining because let's say if you have today 5 gigahertz processor,
Yeah.
which means 200 picosecond cycle time, the actual calculation is less than 100 picosecond, less than half the time, and remaining half the time is used to get the data from previous execution unit where they needs to be consumed. In our case, we basically split that into 2 separate steps, which allows the higher clock speed, not necessarily more performance. And then where the compilers and other technology comes, where in 93% of cases, on average, we are able to eliminate the moving the data from previous execution unit to next, which improve the speed because we don't need to do 2 steps, we do only 1 step, but it also dramatically reduce the power because we don't need to send the data across the wires.
All right. So a lot about actually keeping data local, even within regions on the chip itself. A lot of optimization went into that. Let's, we don't have a whole lot of time. Tell me, what's the form factor? How are you bringing this to market? Am I going to be able to buy one of these for my MacBook and plug it in, or how's this? How are people going to experience Tachyon?
Sure. As we mentioned, we are not targeting consumer electronics, so we'll be not in the laptops, we'll be not in the phones, we'll be in servers, and we'll be bringing into two forms. In the forms of server, one for air-cooled systems and one for liquid-cooled systems. And liquid-cooled systems, there is a lot of interest because the hot water from liquid-cooled system can be used and energy reused, reducing the cost of operating system. So the liquid cooling has a lot of green aspect by ability to reuse hot water instead heating water by gas or electricity.
All right, so we can even recover some of our energy loss here and fight climate change. I know we talk about high utilization of this. Somebody looking at a huge server farm of these can run all sorts of different workloads round the clock using different combinations of workloads on the same chip now instead of having to have different dedicated machinery that might sit idle when that workload's not idle. And so there's a lot of
And good
convergence.
example is Facebook,
Yep.
where when people are sleeping, 1 a.m., 2 a.m., a lot of servers are turned off, majority of them to save the power, but then AI, which is training AI, is running 24 by 7 on specialized chips,
Yeah.
typically NVIDIA GPUs. You can use same equipment for that. You don't need to turn off the servers and you can use them for AI and you will get 10 times more AI without buying any additional GPUs.
All right. So just to summarize here, Rado, you've got a new chip architecture. I can't believe we're even talking about this. You've got something that the hyperscalers, large enterprises are going to be able to use to completely optimize their server infrastructure and to compress the utilization of it. We talked a little bit about the density of supercomputing farms can footprint wise can drop tremendously, and then we talk a little bit about this performance increase that you're bringing along with this, not to mention the infrastructure shrinking and unifying, but the performance going way up to 90 teraflops. I think you said that, which is an incredible thing. Uh, Tell me a little, just finally, when is this hitting the market? When are we going to be able to get our hands on this?
So the sampling is targeting December of this year, and it should be in market in first half of next year, kind of similar time when Grace from NVIDIA, which was pre-announced, will be targeting the market. So first half it should be in volume production.
All right, so a lot of people might watch this and become very interested in learning about what's coming because there's been RISC, there's been ARM, there's been x86, and now there's a Prodigy here. This architecture. People are going to want to learn about this. Where would you send somebody to start digging into this to learn more about what you're building?
Yeah, basically on our company website, www.tachyum.com, which is tachyum.com. You can find various sections. You can see the video from our FPGA emulation demonstration. You can see demonstration of various software, how x86 binaries can be run, how ARM binaries can be run, what kind of market we are targeting, executives and people within company, and a lot of information they should be able to find there.
Oh, this is amazing. I thank you so much for being here today and having the patience to walk through some very technical topics with us. And just it's great talking to you again. And I hope we can meet again more than in person this year or next year soon enough
Yeah,
again.
I hope so too.
All
Thank
right,
you very much, and to all listeners.
and take care out there. Check out Tachyum, and it's a brave new world. We've got new chip architecture coming for you. Take care.